Konnichiwa, Zamurai Engineer. In this video, let us go to the next chapter which about nonlinear equations. So nonlinear equations is a big problem in practical application. And we will start with module number 1. So the module number 1 is about bisection method. So let us start. Bisection method. What is the basis? There is a theorem in mathematics which says an equation fx equal to 0 where fx is a real continuous function has at least one root between xl and xu. Okay. If f sub x sub l, f of x sub u is less than 0, meaning if you multiply the value of fxl multiplied by fxu, this value is less than 0. So if that is less than 0, then that given function fx has at least one root. Okay. So for example, we use xl as the lower value between the two, and xu is the upper value between the two. As you can see in the figure, we have what? X-axis and fx-axis. So fx-axis is the value of the function, meaning the vertical amount, the vertical quantity. So meaning if we have fxl, that is the height of the function from this point to this point, corresponding to xl. And fxu is the amount of the function or the height of the function here. So meaning from this point to this point. You will notice that the value of the function at xl is negative because it is going down, and the value of the function at xu is positive because it is going up. Or yes, it is above the x-axis. So therefore, going up is positive, going down is negative. If you multiply negative times positive, the answer is negative. And therefore, any number with negative sign is less than 0. Okay, so very clear. It is clear that this is satisfied. This condition is satisfied. Okay, since this condition is satisfied, the theorem says that at least one root at least the equation has one root. That is the statement of the theorem. So there is one root. There is one real continuous function and one root between xu and xl. So in the figure, the intersection of the curve is what we call fx, and its intersection with the x-axis, this is what we call the root. This is the root of the function. So this point here, the intersection point here, this is the root of the function. As you can see, there is one intersection, and therefore we can say that there is one root. And therefore the theorem is satisfied because there is one root between x, l, and x. It is very logical if you just think about it, because if the function is negative on one side and the function is positive on the other side, the function will definitely cross the x-axis, and crossing the x-axis is what we call root of the function. Okay? So in the figure, at least one root exists between the 2 points if the function is real, continuous, and changes sign. Changes signs. So the function initially is negative and then it became positive. The function is negative here because the function is from 0 going down. That is negative. From 0 going up, that is positive. So it changes the sign from negative to positive. Okay. So the condition of this theorem are all satisfied. Real, continuous. The function is continuous because you can see the curve is coming from this point up to that point. That is continuous function and also changes sign. So you can repeat and repeat, rewatch and review this theorem because it is very important for you to understand the concept. This is a very basic concept which I think already introduced to you during your first year or even senior high school because it is an algebra theorem. Okay. Continue. Let us again discuss. There is now another type of function. In this figure, if function fx does not change sign between 2 points, roots of the equation fx may still exist between 2 points. As you can see, fxl is positive because it is from 0 going up. This is a positive amount. You can see this is 0 and going up positive fx. This means positive fx. So from 0 positive fx. So from 0 positive fx. So positive is the correct sign of fxl and also the correct sign of fxu is also positive. So there is no change in sign. So positive times positive is positive. But our graph shows that we have what? Roots of the equation. We still have roots of the equation. But now the root is not 1, but there are 2 roots. What are the roots? Between. The roots between xl and xu are this point and this point. Those are the intersection points between xl and xu. Of course, as you can see, we have another root here, but this root is not between xl and xu. Okay? Okay? Do you understand that it is very important to have a definition of domain? Domain is a technical term that you already learned from senior high school, grade 11. Okay, the domain. This is what we call domain, from XL to XU. Okay, so if function fx, okay, let us clarify further and repeatedly clarify it in order to erase the doubt and erase the doubt. Let us clarify. If function fx does not change sign between 2 points, so point xl and xu, here this point and this point, they are both positive. The function is positive at that point. We are not talking of the sign of xl and xu. XL and XU are both positive, but we are not talking of the sign of XL and XU. We are talking of the sign of the function. Function at XL, function at XU. Okay? Roots of the equation fx may still exist between 2 points. So, but now, you will notice there are 2 roots. In the figure number 1, previous slide, we have 1 root. Okay, because the function changes in sign, and therefore the theorem is correct. Theorem is correct. So let us consider again. Figure number 3. If the function effect does not change sign between 2 points, there may not be any roots for the equation. There can be roots and they may not be any roots at all. So there are two possibilities. So in this figure, between XL and XU, both positive value of function here, 1, 2, they are both positive, and they are both negative here, going down, negative. But between these two, there are no roots, meaning there are no intersection to x-axis. There are no roots. There is no intersection of chord to the x-axis. So another thing is that if the function do not change in sign, it could have roots and it may not have roots. It may have or may not have. So it is not very clear. We have to verify it. However, if the function changes its sign, it is sure that there is at least one root. So it is what is the beauty of that? Because we do not have to clarify. We do not have to verify. We already know that there is at least one root. We already know. Unlike if the function did not change in sign, we are bothered if there are roots and if there are no roots. We should be bothered. But and what we'll have to do? We have to verify. That is the work. That is the good about Turing. It makes our life easier. So if the situation says that the function changes sign, we already know that the function has at least one root. If the function is continuous within valid regions, okay, so we don't need to verify. Unlike if the function did not change in sign, we are bothered and we have to verify if the function has a intersection with x-axis or not. In other words, if the function has roots or not. Okay, that is the conclusion. Another case, if the function f(x) changes sign between 2 points, it changes sign. So xl from 0 going to positive. So the function is positive. xu from 0 going down, the function is negative. So the function changes its sign from positive to negative. Okay. What can we conclude? The function has more than one root. Okay, more than one. And if you can count between XL and XU, you can say 1, 2, 3. There are 3 roots. Okay, so there are 3. It is possible that there are odd number of roots if there is what changes in sign. If the function changes in sign from negative to positive or from positive to negative, like this one, it is possible that the function has odd number of roots. Therefore, the statement of the theorem that the function has at least one root is correct because 1 is an odd number. Okay, odd number of roots, 1. It could be 3, but at least 1. Okay, so in this example, it is 3. There are 3 roots. There are 3 roots in this example, but at least 1 is enough. Okay, so if you want all the 3 roots, you can verify. But if you don't need it, you can just believe and use the theorem in order to be sure, you're confident enough that you can say there is at least one root. There is at least one intersection with the x-axis. Okay, so this is the algorithm for bisection method, meaning the procedure. Algorithm is a procedure. It is a step-by-step procedure in order to accomplish a certain operation. So we want to do the bisection method operation, so we want to follow this procedure, step-by-step procedure, meaning algorithm. Algorithm step 1. Choose XL and XU as two guesses. Guess. You are not sure. Just give a number. Just give a number. There are two types of guesses. There are wild guess and scientific guess. We want to be able to give scientific guess because we are engineering. We want to use science. Okay? Science in mathematics. So we want to have a scientific guess, not wild guess. So let's choose XL and XU as two guesses for the root, such that if we multiply function fxm times fxu, the answer is negative or less than 0. Or in other words, fx changes sign between xm and xu. This was demonstrated in figure number 1. Okay, so we must have two guesses. Okay, if you guess one and evaluate the function and the function is positive, give another guess. If the function evaluated at that guess point is another positive, then don't use that. Try another value for x and substitute to the function and evaluate again. Then after evaluating, if the result is negative, that is the one we needed because we already have positive as our first evaluated function. So positive and negative. So it is enough. We already know that between that function, between that domain from x1 and x2, we know that there is at least one root of the function. Take note of the condition. Okay? Take note of the condition. There are what? Condition that the function is continuous, like this, continuous. There is no jump, there is no void, there is no vacuum points. So it is continuous, particularly between XL and XU. So that is our step 1. You have to make a choice. Just select two values of x, one of which is XL, one of which is XU. Just select two points. And you can try it again if it did not went good, or if it did not satisfy the theorem. So we need to be able to evaluate two values of functions which are different in sign. One should be negative and the other should be positive. Okay. If did not happen at one guess, try another guess, and so on until you satisfy that condition. Okay, so that is step 1. Going to step 2, let us estimate the root xm of the equation fx is equal to 0 as that point between xl and xu. Between. If xm is between, therefore we can just what? add XL plus XU and divide by 2. Okay? Because XL and XU are two distinct numbers. If you average, so it will become the midpoint of the numbers. It will become the midpoint, and we have to use that midpoint as our step 2. Computing the midpoint is our step 2. So let us test what? XL plus XU divided by 2. As you can see in the figure, XM now is what? Nearer to the root. Right? Take note. Our problem is finding the roots. Okay? Finding the roots. And we have what? Given continuous function. Okay, so let us go to the next step. Now, check the following. Okay, use the midpoint x value or xm and substitute it to the function. You can evaluate the function using x sub m. And then use that x sub m, multiply it to xl, and check if the product is less than 0 or if the product is negative. If the product is negative, then the root lies between XL and XM. Okay? So that is our check. We have to check. No? And if that is the case, therefore, let us make the new value of XU, the upper limit of XU. What is now the new value for the upper limit? Use the value of XM to be the upper limit. Okay, but if we multiply FXL times FXM and it results in negative in positive, then the root lies between XM and XU. If the answer is positive, and then do the following: XL is equal to XM and XU is equal to XU. Okay, so meaning to say, we change the value of lower limit XL to be the new value of lower limit to be the midpoint value. Okay, and case number 3, if FXL multiplied by FXM is equal to 0 exactly, then we are lucky because XM is actually the root of the function. So we are through with the procedure. We already found out that the root is XM if this is the case. Okay. Okay. So, step 4, if the new estimate of the root xm is equal to xl plus xu divided by 2. So, find again another value of midpoint. So, we already repress the value of xl and xu based on step 3. And then repeat the solution for xm, which is again the midpoint of the current value of xl and xu. And find the absolute relative approximate error. So we have to determine if our value for xm is already acceptable. So xm old, xm new. That means previous estimate of root, current estimate of root. So it depends on how much accuracy do you want our root should be. So if you want higher accuracy, then you can iterate, you can repeat the process. Find again another new estimate for XL. And it is easier to find that because it is just the what? The average of XL and XU. Okay. So step 5, compare the absolute relative approximate error. We already know how to calculate absolute relative approximate error. Okay, this is the formula. Okay, what is that? Absolute relative approximate error is equal to x nu minus xm nu minus xm all divided by xm nu times 100. So that is our definition. We already explained that on chapter 1. So please, if you want to review, go back to our video lectures on chapter 1. So it depends on our pre-specified error tolerance. So if we have an specified tolerance, epsilon s, so there will come a time that our result absolute relative approximate error will be less than the tolerance, the pre-specified error tolerance. If that is yes, meaning if our calculated absolute relative error is greater than pre-specified tolerance, epsilon s, then let us repeat the process. Go to step 2. Okay, again. But if the pre-specified tolerance is greater than our calculated absolute relative approximate error, let us stop the algorithm. And the value of xm is our root of the function. Okay, it is clear that we will have the answer for the root of the function. Note that one should also check whether the number of iterations is more than the maximum number of iterations allowed. If so, one needs to terminate the algorithm and notify the user about it. There are times that there is no stopping the procedure. Always the answer is yes, and also okay, the answer do not change. The answer of the iteration just go back and forth, and do not settle down. And therefore, if the value that we are calculating do not settle down to the point, there is no trend going stable. There is no trend, so it will go on forever. If you feel that the computation will go on forever, going back to step 2 and 3, 4, step 5, then again step 2, and so on, then just have a maximum number of, just set a maximum number of iterations. For example, set maximum iteration number to, for example, 8 or 10, maximum. Okay, and then stop it after you observe that there is no stability. Okay, the procedure do not go to a certain value corrects. Okay, that is not usually the case, but in case that happens, you have to be able to stop the algorithm. Okay, for example, we have here an example for Down the Toilet Company that makes clothes for ABC commodes. The floating ball, these are name of the company. Okay? And the floating ball has a specific gravity of 0.6 and has a radius of 5.5 centimeter. Radius 5.5, specific gravity 0.6. Okay. What do you mean by specific gravity? Okay. So we already know that in our science and physics. Radius, what do you mean by radius? We already know that in our geometry. So 5.5 centimeter. You are asked to find the depth to which the ball is submerged when floating in water. Okay. So if we take this ball with this type of property, 0.6 specific gravity and 5.5 centimeter radius, and submerge it into water, what will happen? That is the question. So we have a diagram here. Diagram of floating ball. We have radius, that is 5.5, and we have water, and we have x. X is the value we want to know. Okay, that is the depth to which the ball is submerged in the water while it is floating. So let us analyze the problem. The equation that gives the depth x to which the ball is submerged underwater is given by this is the equation. Okay, using our mathematics and physics combined, we have this equation. It is now given x cubed minus 0.165 x squared plus 3.993 times 10 to the negative 4 is equal to 0. Okay, we already know what is the meaning of x. That is a variable which is the depth wherein the ball is submerged while floating in the water. So let us use the bisection method of finding roots of the equation to find the depth x to which the ball is submerged underwater. Conduct 3 iterations to estimate the root of the above equation. So we are told to have 3 iterations. It is specifically asking us to have 3 iterations. So find the absolute relative approximate error for letter B at the end of each iteration. Let us compute the absolute relative approximate error and the number of significant digits at least correct at the end of each iteration. So in order to know that, we know that we have what? We have a criteria for the number of significant digits sure to be correct. That is what? 0.5 times 10 raised to the exponent 2 minus n, where m is the number of significant digits. Okay, so let us solve this problem. So from physics of the problem, the ball would be submerged between x is equal to 0 and x is equal to 2r, because 2r is diameter. So that is our domain. X can only be 0, and of course x cannot be negative, because if x is negative, that is not just floating in water, that is floating in the air above water. Right? So there's no meaning to it. There's no meaning for x negative. The x value would start at 0 up to the diameter, which is 2r. Okay. So therefore, if the value of radius is 5.5 centimeter, that is what? 0.055 meters. Therefore, we know that x is between 0 and 0.11 meters. So our unit of measure here is meters. So x is in meters. Okay. So let us continue our solution. So to aid in understanding of how this method works to find the root of an equation, the graph of fx is shown to the right. So this is the graph of the function. What is the function? Fx is equal to x cubed minus 0.165 x squared plus 3.993 times 10 to the negative 4. If you graph that equation, the red curve here is the function. Okay? Okay? You can use Excel or you can use manual. Tabulate x value and fx value, x and fx coordinate. Do several computation. So you can have 10 to 15 coordinates and then plot the key points and then connect the dots, connect the points. Okay, so that is how we can draw this graph of the function. And it is clear to us that from x value of negative, there is no meaning. The x should start with 0 up to certain point, 2.11. And as you can see in the figure, 0.11 is about this point. This is the 0.11. It is a little bit bigger than 0.1, but it is far away from 0.12. Okay. Okay, 0.10, 0.12, so in between. It is in the middle of 0.10 and 0.12. That is 0.11 here. So in the middle. Okay. So from zero to that point, you will notice that there is one cross intersection of the curve to the axis, and that is the root. We want to find that value. Okay. So let us assume XL is equal to 0 and XU is equal to 0.11. That is the what? Extreme. That is the extreme of the valid domain, because the value of valid X is from 0 to 0.11. So that is the extreme. So if you evaluate that, you will have the following answer. So XL, X is 0, so make all the X 0, so you have 3.993 times 10 to the negative 4. And if you have 0.11 substituted, so you have negative 2.662 times 10 to the negative 4. So the function now has what? Different sign. One is positive and one is negative, and this is what we want. Our first guess, which is what? 0.00 and 0.11 is a good first guess. Okay? Actually, good first guess. We already saw the graph. So therefore, using that, we can what? Solve. We can solve the midpoint, because we already know that if we multiply this function, the answer is negative or less than 0, and it satisfies the theorem. Okay. We know that there is at least one root between XL and XU that is between 0 and 0.11. So let us go to the graphical. So we solve this x0, we solve this value. How much is this value? From 0 to this one, how much is this value? We already know. We already evaluated that. That is what? 3.993 times 10 to the negative 4. That's the value there. How about this one? This is 0.11. So if we substitute, we can evaluate the value of the function here, and the value of the function here is negative, which is equal to what? Negative 2.662 times 10 to the negative 4. Okay. So we are able to demonstrate the sign changes from positive to negative. And let us follow the procedure or the algorithm. So let us calculate xm or the midpoint. So just take the what? The midpoint or the average. 0 plus 0.11 divided by 2 is equal to 0.055. Now substitute the value 0.055 to the function so that we can evaluate fxm. So here, so we have fxm. Substitute to the function, and the result is 6.655 times 10 to the negative 5. Okay. What is this? Is this a positive or negative number? So if we multiply it to fxl, the answer is positive. So therefore, we will use the value of xm to be the new value of x lower. Okay. So our xl should become the new value xm, which is equal to 0.055. Because of this, because the answer to this multiplication is positive. Okay, so we have to replace the value of xl to be the value of the xm. That is our step 2. That is our step 2. So take a look at our algorithm. So at this point, the absolute relative approximate error cannot be calculated as we do not have previous approximation. Okay, we need previous approximation. We only have first approximation now. So let us iterate to the next. Now we have 0.55. So 0.55 is here, about here. Okay, so therefore, iteration number 2. Again, let us average 0.055 plus 0.11 divided by 2. The answer is 0.0825. Now, again, use this value and substitute to the function here, substitute to the function, substitute, and evaluate. Now, the answer is negative. Meaning, if we multiply this function to the value of fxn, the answer is negative and therefore less than 0, and we satisfy. Okay, so therefore we know that the root is between 0.055 and 0.085 because of this, because if we multiply, it becomes negative. It changes the sign. So we have to replace the value of new upper limit for xu to be 0.085. And that happens here. XL retain 0.055, XU change it to 0.0825. Notice from the domain become smaller. It will become smaller and smaller up to the point that we can find the root of the equation. But now we are just limited to 3 iterations. This is the second iteration. So let us go further. Okay, so 0.0825 and 0.55 here. So that is our here, the green one. The green one is 0.55. The blue one is the 0.0825, the new upper limit. So this is the first lower limit, the current lower limit, the first upper limit, the current lower limit. So it becomes what? Nearer and nearer to the value of, or to the intersection, or to the root. Okay, so again, let us find the absolute relative approximate error. Okay, we can do it because there are what? There are two values, XMM new, XMM old. So there are two values for our XM. So, therefore, if you compute this, the answer is 33.333%. Okay. Okay. None of the significant digits are at least correct in the estimated root of. Okay, none. Because 33% is larger than. So our criterion is 0.5 times 10 raised to the power of 2 minus m. 0.5. If m is 0, so 10 raised to the power of 2 is 100. 100 times 0.5 is 50. So 50. 50 is still larger than 33. Okay. 50 is larger than 33.33. Okay. So because it is greater than 5%. Okay, so one significant digit, because 50 is greater than 33, 0. 0 significant digit, because if one significant digit, that is 1. So 2 minus 1, that is the exponent. 2 minus 1 is 1. 10 to the 1 is 10. 10 times 0.5 is 5. That's why it is 5% here. This written statement. And 5% is smaller than 33 point. So therefore, 5% represent one significant digit. And since what we calculated here is 33, there is no significant digits. There is no correct in our answer. So let us go to the step number 3. Again, find the XM to be the average. Okay, the average is 0.06875. And then again, do the same iteration. So put this value, substitute it to the value of the function. Okay, so you can evaluate the function here. And the value is negative 5.563. Therefore, if we use this and multiply to FXL, we can see that the product is negative or less than 0, because negative 5.5, 63 times 10, negative 5. Okay, this one times 6.655 times 10 to the negative 5. The answer would be negative. And since the answer is negative, it is less than 0. And we satisfy the theorem. Therefore, we know that the root is between these two. The root is between these two. What is this two? This is 0.055 and 0.06875. Okay, so it is written here between 0.055 and 0.06875. We already know that by mathematics. Okay, so let us look. So it is shown like this: 0.055 and 0.06. The blue one is the 0.06. So the blue one is the 0.06875. So our root should be between this green and blue one, and that is near to the value of the roots. Okay, let us go further and calculate the absolute relative approximate error. And that means new XM old XM divided by new XM. So using these values, you can say that the answer is 20%. And you will notice, still, this is greater than 5%. So therefore, none of the significant digits are at least correct. Okay, so 7 more iterations were conducted, and this iteration is shown in table. We have 3 iterations, and the problem made another 7, so total of 10. That's why I gave you the idea. 8 to 10 iteration is good. Okay, in order to find precise answer. Okay, so there are 10. Okay, we initially do the 3 iteration, then just show you the last 7 iteration. Okay, so as you can see, the absolute relative approximate error became smaller and smaller, and at the 6th iteration we now have what? 1 significant digit correct here, because it is less than 5. This is the time it is less than 5. We have 1 significant digit correct here. What do you mean by that? What do you mean by that? This value 0.06359 is not very accurate. We can only be sure that 0.06 is correct. Okay? 0.06 is correct, but we don't know if 359 are also correct. We still don't know. Okay? That is the meaning of this. Okay? Okay? So if we use again the 7th iteration, still we only know up to 6. 1 significant digit is 6. The significant digit is 6 here. Again, still we don't know, only the 6 is we are sure about. But after the 9th iteration, it is less than 0.5. Okay? 0.5 is actually 2 significant digits. What is the supposed answer? 0.062. We are very sure that 0.062 are the 2 significant digits correct. Okay? So up to the 10th iteration, we still have the same 2. We have the 2 significant digits correct. That is 0.062. So our answer should be 0.062. Okay? Okay? That is our root of the function. Okay? So this is how we estimate the true value. Maybe we cannot, it's very hard to get the really precise answer, really accurate answer, but still there are level of acceptability. So this 9th iteration is already acceptable for 2 significant digits, meaning 0.062 is the correct answer. But if we are talking of 3 significant digits, we can still iterate further. Maybe, in my estimate, maybe 13th iteration if you want 3 significant digits. But if you only want 2 significant digits, stop in 9th iteration. 9th iteration is okay. We are sure that the answer is 0.062 to be our root of the equation. Okay? If you have any question, you can try to Here's our comment box. So here's the number of significant digits at least correct is given by this one. So we have this criterion. So remember our criterion. So M, okay. So M is equal to 2. So there are 2. The number of significant digits at least correct in the estimated root is root of 0.0624110 is 2. There are 2 significant digits. That is 0.06 and 2. So doing this type of method, or the bisection method, what are the clear advantages? They are always convergent because we are going nearer and nearer to the correct answer, to the required answer. We are closing in. We are closing into the correct number. So because the lower limit of XL and the upper limit XL are closing and closing on each other. And the correct answer is in between. So if XL and XU become very small, therefore we can be sure that the answer is almost that any of the XL and XU, or actually the midpoint or the average of XL and XU. And number 2, the root bracket gets halved with each iteration. It is guaranteed. Okay, so these are the obvious advantages of the method. What are the drawbacks? Very slow convergence. Very slow. We need what? 10 iteration and we only are sure for 2 significant digits. And in my estimate, 13 iteration to be able to be sure for 3 significant digits. It is very slow. No? We say it is slow because we have other methods that are far more faster than this. If one of the initial guesses is close to the root, the convergence is slower. So this is one of the drawbacks. Although you can be sure that it will give you the correct answer, it is very slow. But since you are using computer anyway, you are using computer, you are not doing it manually. In our time, our scientific calculator is not given at the level of the scientific calculator today. Our scientific calculators, the most important function are sine, cosine, tangent, logarithm, natural logarithm, and what? Square root. There are no cube roots in our calculator. There are no other roots. So it's very hard during our time. You have to do it manually also. There are no windows. There are no windows during our time. Our operating system is MS-DOS, or what we call disk operating system DOS. Okay? So it's very slow. But if you use laptop, computer, apps, it is also fast. But if you try to compare this to other methods, of course, this is slow. Another drawback, if a function is such that it just touches the x-axis, it will be unable to find the lower. You cannot have an upper and lower guesses because all of the value of the function are positive. You cannot have the positive evaluation of the function and the negative evaluation of the function. You cannot have that. Because if you evaluate the function at any given x, from this point to this point, they are all positive. From this point downwards or negative side, always positive because it is going up. Positive here, positive here. All of the values of the function are positive. How can you evaluate this? You cannot what? Satisfy the theorem. Cannot satisfy the theorem. So that's why. So it is what? Unable to solve some of the problems. Another drawback, function changes sign, but root does not exist. There are times. For example, hyperbolic, like this. This is a hyperbolic equation, 1 over x. Okay? This hyperbolic equation is rotated 45 degrees, 1 over x. One over x do not have function that changes sign also. So very difficult. There are practical difficulties in applying the bisection method. But anyway, most of the functions could be solved by the use of this method. Okay, anybody, please review this method. It is an important one. It is the very basic method. And see you on the next video. Again, this is Dr. EYPEI, Teaching Engineering for Nation Building.